it should be going within the next second or two. So, oh, well, thanks, Lucy. I needed that. So this is super. Okay, this is the most important thing you guys are going to do in all of college. All right. So, is there going to be a practice quiz for quiz 5? There will not be, but I will tell you two things. Right. I'll tell you two things that will help you out tremendously. One is that it's postponed until next Tuesday. So how's that? Like that just right off the bat. And the reason is not because I won't get through the material the day that you need for it. Ultimately, you will, like we will, and you guys will see it. What it is that I'm just going to simply ask you guys about interpretations of linear or nonlinear models, right? We see it up on the screen here. We're going to go through the different log regressions. I just don't want to rush through it. You guys have done it on your lab, and so what you're going to have is the way that I thought about it in my head. We're going to talk about log regressions today. You've done them in your lab. You're going to turn it in this weekend for lab number 4, and then you'll have your quiz due on Tuesday. And I think there's just kind of a natural progression of that. We'll have kind of moved on a little bit from that by Thursday, but I don't want to rush through it, and that's my one piece of like good news. The other piece of good news is I was looking at just what this class entails for the rest of the term, and I'm in kind of like a weird spot, and a lot of it is because that Thursday was off, and usually I'm kind of like rushing to finish up a thought by the end of the term, and that's not going to happen this term. I'm essentially like, when I look at what you guys have left, we've got lecture quiz 5 that'll be due in a week from today, lab assignment 4 due Saturday. You have your next lab assignment, you'll do that over this next set. That's not going to be due till December 4th. Your last quiz isn't due till the day of the final, and then there's the final. We were really front loaded in this class. That's why you guys were probably like, my gosh, this class just keeps coming. There's just stuff and stuff and stuff. It's all going to be kind of like, you're kind of getting rewarded now because we're really on there's a soft landing to the end of the term. Okay. So, it doesn't mean you should take your foot off the gas or anything like that. You want to dedicate a lot of time to understanding and whatnot, but you're certainly not going to just see assignment after assignment coming at you down the home stretch here. So those two things I think will hopefully just kind of ease your stress a little bit, because again, I want to go through at a pace that I think is appropriate. And that's, again, the most important thing to me. We're going to hit the amount of material that I want to hit. I can see it already. And maybe we'll all meet up on campus on the last day and have donuts or something. I don't know. Right? That's like kind of how I feel. Like it'll be kind of, again, just a light finish. Okay. So any questions, any thoughts, feelings? All right. So let us get rolling for the day. And hopefully you guys will just see the applicability of this class just go up as we move into more stuff, the last stuff of the term. Now, if you guys are thinking about taking 108 in the spring, what you're going to want a good reason to feel comfortable about this stuff is this is essentially where we start 108 with kind of this kind of last week or two of 107. That's going to be the review as we go into 108, and you'll see why. Because ultimately, what we're trying to do is we're trying to solve the problem of the expected value of u given x not equaling 0. That's going to be what 108 completely is revolved around. And this polynomial regression gets right at that. Yeah, I'll be teaching 108 in the spring. And so that's, to me, that's, it's funny because the chair asked me if I wanted to teach it. I wasn't originally scheduled to teach it this spring. I've taught the last 3 springs, and the chair said, would you want to teach 108? I kind of think you want to teach 108 this spring. He asked me like earlier in the term. And I was like, it's fine if it makes your life easier. I'm pretty indifferent. And then I started teaching 107. I'm like, no, I want to teach you guys 108 too. Like I want to keep the train rolling. Like I think it'll be really great to just keep this going. Having a term off or taking time series and then coming back to 108, like I think it's a really good. It really sets you up well. So I'm really happy to do that. So okay, so with our polynomial regression, right? Oh, thanks, Leslie. You guys are being so nice today. It's really nice. I like this class too, right? And I think we're getting into the great stuff, and one of it is just right up on the screen here, right? Because we have this data that we know is not linear, and it'd be weird if the world worked in a linear fashion, right? If every relationship that we ever saw was linear, that doesn't make any sense, right? So we need to adapt our models so that we can actually fit data that isn't linear, but is in fact more realistic, right? And so what did we do last class? We really got into this polynomial regression. And a great benefit of this polynomial regression is that it fits this nonlinear data so well, and it's easy to implement, right? And so last class we had the do file that was just like, hey, we've got average income, let's just do average income squared. We're all set, right? And with that in mind, let's go ahead and I'm going to start up a Stata file because again, I think that's going to be what 108 is all about. So we're going to start to see 108 kind of come about right now, and what kind of the average day will look like will be exactly this. So we know the drill here, right? We know we want to put that up here. We're going to clear. All right, we're going to change directory. Right, I still don't have my directory memorized, so and I don't know if I need to. I probably should just copy and paste all the time. Right, so we got change directory, use California school .dta, right, and then I'm going to log or cap log close, log using lecture 14, comma replace, log close at the end here, and then summarize. And so hopefully by me doing this, I know it's a little redundant and it can get a little bit like boring to some degree. I totally am on board with that, or understand that. But again, it's a language, right? And so just the more that you do the repetition, the better you're going to get at it, right? So just doing this simple command right off the bat, I think it's really helpful just for all of us, especially as we continue to just get more comfortable with Stata and just programming more generally. So we've got our stuff out, we've got our data loaded, right? And let's go ahead and let's just do our scatter plot, right, of test score on average income, right? And we can just do a two-way scatter of test score and average income, so average income, right? And just take a quick look at that, right? And we know, right, we knew from last week, we saw it up on the screen, you can plot your data and be like, this, a straight line ain't gonna work here, right? And you can alter your do file to really highlight that and say, I'm not only gonna have a scatter plot, I'm going to have a linear regression in LFIT go through this and show that this is not appropriate, right? It's not drastic, right? But just look, our expected value of u given x isn't equal to 0. We can see it right here. All of these errors are negative. All of these errors are negative. Lots of these errors are positive. Right here, this range right here is only positive, right? So we certainly don't have equation or assumption 1 satisfied. So if we were to have a Q-fit, all right, well, what exactly is that doing? Well, first, let's just take a look at it, because if we just type in Q-fit, we can thank Stata for making this easy for us, right? I'm going to make this big, all right? So we've got the quadratic fit, or that polynomial regression, right? That's really, again, there's a little bit of this expected value of u given x not equaling 0, but certainly a large improvement over that linear fit, right? So even way out here, right? What's the expected value of u given x given that our average income is 50 or 60? I mean, we're hovering right around 0, right? There's not, even at 40 for sure, right? That distribution looks like it's centered right around 0. And I think that's really, just in a picture, what's kind of neat to see, all the work again that we've done on the back end, right, comes out very, very nicely when we see it in a scatter plot here. Okay, so when it comes to the implementation of this, right, this line right here, what exactly is this line? That line is test score equal to beta 0 plus beta 1, average income plus beta 2, average income squared, right? So we need to be comfortable regressing our test score on average income and average income squared. So this means, right, that we need to actually generate a new variable, so average income 2, which is equal to average income squared, okay? So then when we run that regression, we can just regress our test score on average income and average income 2, right? And again, I told you guys last time we could just go ahead and put an asterisk there. That's going to be the same thing, comma robust, outreg 2, using lecture 14, comma replace. We're good to go, okay? So we can go ahead and run that regression. We interpreted this last time, And the thing that's nice about this, like I said, is how easy is that to implement, right? So we kind of went from this nonlinear world to this, or this linear world to nonlinear world. Just, I mean, ultimately, like a few straightforward commands, I think is ultimately what it is, right? So that's the benefit of it. That's the pro, right? The con, though, is that this is really difficult to interpret, right? Because when you look at this, right, and we just look at these results right here, we've got this 3.85 that we wrote down last time. So we increase average income by one, or $1,000. Test score goes up by 3.85 points. That's the easy interpretation, right? That's not where we struggle. Where we struggle is right here. So average income squared is negative 0.04. Like what? Like you can only even like it's hard to even like envision what that means. And that's really where the difficulty of these polynomial regressions come in, is that in order to interpret the effect of a change in income, we need to go to each specific change in income. So we went from $10,000 to $11,000, I think, last time, and then we went to 40 to 41, or some number along those lines. We're actually plugging in values, right, of X in order to get the total effect of our change or total change in Y. So I kind of was just writing stuff out and just throwing numbers out here, and I kind of want you guys to just again, I do like to give you guys a sense of how I approach questions just on this topic, because it is so abstract, right? So another example I could use is imagine I gather data on GPAs. So run GPAs on study hours and study hours squared. So what am I trying to highlight here? I am trying to highlight you should study, but you shouldn't cram. That is exactly what this is saying. And we can see that. We can see this come out here, right? So your GPA, if your study hours per week, right, is 5, right? So you're studying 5 hours a week. I should have probably changed the magnitude. You guys should study more than 5 hours and 10 hours. But the point is that if you study 5 hours a week and you go up to 6 hours a week, what happens to your GPA? All we've got to do is plug in 5 for study hours and then 25 for study hours squared, because it'd be 5 squared. And what we get is 3.15. Oh, I should give you a boost there. I'm sorry. That was kind of mean. All right. This is 3.6. 3.68. And then, that was mean. I was like knocking you down big time there. All right. So if you study for 6 hours, right, your GPA is going to be 3.678 versus 5 hours, it's going to be 3.6, right? And so you'd say, okay, that extra hour of study per week, that's going to bump me up by 0.078. Like that's a good deal, right? That's potentially worth it, right? And so maybe this is more appropriate for high school, because I feel like in high school now the GPAs are like 7.2 or something like that. So here, if you're studying 10 hours a week, you get a GPA of 3.95. If you study an extra hour, there's a diminishing return to that hour, because again, you have an increase in GPA of 0.053. So if you increase study hours when you have a low study hour, right, 5 hours, go to 6 hours, yeah, you get this kind of nice 0.078 bump in your GPA. If you go from 10 to 11, right, you go up by 0.05. If you go from like 20 to 21, right, you may actually go down, right? You might start to see this start to go negative, because what's the implication of the nonlinear regression result here, right? The implication is that too much studying can eventually decrease GPA, right? That's the idea, right? And so we can see that come out of this particular example that I made up, right? Obviously, I was just making this up to, I don't know, I guess I have some sort of subconscious messages, right? I don't know, right? But you guys are here, you guys are all studying, it's fine. But the point is you can imagine, right? Remember those tests that you've had that you studied 80 hours this week for this test, but then you still didn't do well? Well, that's because those like last hours you weren't getting anything out of it. In fact, you might have just been losing out on sleep. You should have probably been just sleeping instead, right? And studying a little bit more methodically throughout the term, right? And if that's truly the case, you should be able to see that in the data, okay? All right. So fine to fit the data that way. There's no problem with fitting the data that way. However, right, the issue comes up with that interpretation. So I ended last class by saying, can we fit the data but have an easier interpretation? And again, I wouldn't ask that question if there wasn't an answer to it. So the answer is going to come in with natural logs, okay? And so with natural logs, right, there's a lot of properties that I went over that are really kind of slick and helpful, and you've seen those in your different math classes. But the one that we're going to really highlight is that when we look at a change in the log of a variable, right? So it's hard to kind of wrap your head around right now, and we'll see some examples as we move forward. But excuse me, right here, it's saying, look, if we go from x to x plus delta x and take the log, the difference in that is going to be delta x over x, which is equal, right, to the percentage change in x, right? The percentage change in x. Right, so if x is equal to 10 and delta x is equal to 2, right, we can say to ourselves right off the bat that the percentage change in that, right, delta x over x, which is equal to 2 over 10, should be equal to 0.20, right, or 20%, right? This should be a 20% change in our x variable, right? Because we go from 10 to 12, right? So that should be represented by log 12 minus log 10. So let's see this actually happen, right? Let's see this actually happen. So I'm gonna go kind of old school here, right? And actually see this happen, right? So we got 12, take the natural log. This is gonna be 2.484, or we'll do 485 minus 10, take that natural log. We've got 2.30, right? So you got 0.485 minus 2.485 minus 2.30, right? This is 0.8185, right? And so what you should be saying to yourself is like, that doesn't seem like a good deal at all, right? That's like 18.5%, right? Not quite 20, right? Not 20% as we expected. So what I'm highlighting here is that this is applicable for smaller changes in x, right? So this percentage change in x is more appropriate, right? Appropriate when delta x is small, okay? So let's go ahead and let's do, because we can come up with any scenario we want. Let's do, let's say that if x is equal to 10, and delta x is equal to 0.5. Okay, that's something that we can maybe wrap our head around here, and we would say, all right, so then this means that we should say that the log of 10 plus 0.5 minus the log of 10 should be equal to 0.5 over 10, which is going to be about, hold on, let me do that, that's about 5%. Right? So is that what we get? Well, let's take the log of 10.5, subtract the log of 10. Okay. So again, this is like, I would never really do this by hand. I want to show you guys, but ultimately you'll just eventually have this kind of in your mind, right? So so here the log of 10.5, 2.351. We know that the log of 10 is 2.3. That difference, 0.051, this is approximately 5%, right? So kind of neat to see that, look, this is a great relevant quality of, or characteristic of log functions, but we have to make sure that if you're saying, what happens if x changes by 7,000%? It's like, well, I don't know how applicable this is going to be, right? I think you have to just kind of keep all that in mind, right? And that's where folks like to use data to push a narrative. And I think it's more important to say what narrative is the data telling you. Make sure you don't overextend those results, okay? All right, so I'm kind of, really pumping up the tires of the log function. So why don't we actually do something about it, right? I can sit here and say it's a great function all I want, but let me show you what it does, okay? So let's go at a case-by-case basis and say, what happens if we run a regression where we have x in logs, right, and y is linear? So this would be actually the Lin Log Model, right? That's what your book calls it. It's kind of like funny that they call it that. Like I just think of it as y is linear and x is logged, right? But what does this mean? This means that the regression that you're running is y, right? The nominal value of y is equal to beta 0 plus beta 1 log ln of xi. I'll write this nicely. There we go. Plus ui for I equals 1 to n. Okay. So what do we need to do? Well, if we're going to run this regression, right, on Stata, like we're actually going to go ahead and implement this, right, we need to generate log of x. So we're going to generate the log of x by just telling Stata, hey, just like the calculator, just take the ln of x, right, and go ahead and give us log x, right? So we can call a variable whatever we want, right? But we're going to say, let's generate ln of x, which will be log x equal to ln of x. Well, hold on a second. We want to generate the log of average income. Let's go ahead and do that. Okay. So we've got average income. We're going to take the natural log of that. Just call it log average income. Okay. And we can see this being made, right? And so we're going to take the natural. I'm going to go ahead and bring this up here. We're going to take that average income right there and just take the ln of 22.69, ln of 9.89, or 9.8, right? And then 8.9, 8.99, right? That's going to be what comes up over here in that natural log in that next variable. Okay. So let's go ahead and run that. Okay, and there it is right there. Right, so the natural log of 22.69, 3.12, right, 9.824, natural log is 2.28. This is like totally different than like a square root, right? Nobody's like memorizing any of this stuff. There's no kind of like, the only number that's easy to kind of wrap your head around is that the log of 1 is 0, right? But then beyond that, right, it's just being generated by that e function. E is the 2.74, right, raised to the log of x is equal to x. So, so we've got this right here. Now, what you can notice here, right, is that as we change, right, and move along this log average income variable, right, when we go from say 1.88 to 1.99, right, you can start to think about that difference, right? That difference is the delta x, the change in x that we had right here, right? And then that base would be 1.88, so we'd have 0.011 divided by 1.88. That would be the percentage change, right, in that average income. Okay, so we can start to see that come out. It's going to be a little bit more clear when we actually run regression here, right? But that's ultimately what we're doing, right, with this log average income. So now let's talk about the interpretation before we do run a regression. All right, so the interpretation, I'm going to say it right off the bat, and then we can go ahead and dive into it. So ask questions, make sure you're feeling good about this as we move through it. But we're going to say that an increase in this is kind of the first pass here, right? Increase, and this is going to make our life feel easy. An increase in x of delta x leads to a change in y of delta y. So you may be saying, gosh, that's not insightful at all, right? So we change x by delta x, we change y will change by delta y. Here's why I'm bringing this up. So we would say that our change in y, right? Our change in y, we'll put y hat on there, right? This is going to be equal to beta 0 plus beta 1 times the log of x plus delta x, all right? And then the u's will drop out. And then we'll subtract beta 0 plus beta 1 ln of x, right? Natural log of x. Right, so just think about these two snapshots, right? So you think of it as 1.88 and 1.99, right? So we've got a log of 1.88, right? X is 1.88. Then we got a log of 1.99, so you've got 1.88 plus 0.11, right? So we're moving up, right? Increasing by delta x, and that's how much delta y is going to change, right? We just plug that into this equation, right? Our regression equation, and we've got a number, right? So if we were to break this down, we would say, oh, well, the change in y then, right? The betas will cancel out. We'll be left with beta 1 times the log of x plus delta x minus the log of x. Why write it like this? Well, the reason to write it like this, we can just scroll up just a touch, right? I'll come right back down. Log of x plus delta x minus the log of x, that's just the change in x over x, right? That's just the percentage change in x right here. The change in x over x times beta 1, or alternatively beta 1 times the change in x over x, right? However you want to write it. Okay. Okay. So now, right, this is important because it's saying, look, the change in y is equal to beta 1 times the percentage change in x. So how do we actually interpret this? Like, how would we actually implement some numbers, at least in a general sense? And then we'll go ahead and put some real numbers on there. We're going to say a 1% change in x, right, is associated with what? Right? How much is y going to change on average? Well, a 1% change in x, this right here is 0.01, right? That's how much point, that's what a 1% change is, right? 1% is 0.001, right? So then we would say that this is going to be associated with a beta 1 times 0.01 change in y. So if we change x by 1%, that means, right, a 1% change in x means that delta x over x is equal to 0.01. Okay, so I'm going to go ahead and write that out a little bit more clearly, just so you can see it, right? And I'll erase this right here, right? A 1% change in x right here, this implies that delta x over x is equal to 0.01. Right, that should really help you out, right? Because when I say, hey, x changed by 4%, you'd say, oh, well, that means delta x over x is 0.04. So then our change in y is just going to be beta 1 times 0.04, right? Because that's what this is right here. This equation, which again, you guys are probably like, why are we doing this? Like, this seems kind of like it's really just not coming together. Hopefully you're sitting there saying like, oh wait, this is kind of telling me everything. Right, because all I have to do is just say this right here is my percentage change. Then I just multiply it by beta 1. I get my change in y. So that, again, we can go ahead and just take it a step further. What if we have let me do something weird, right? Like a 7% change, right? Right, a 7% change in x is associated with what? Well, we'll say beta 1 times 0.07 change in y, okay? And again, why is that the case? Because the 7% change in x is saying that the change in x over x is 0.07, right? So that conversion there, right, is from that percentage change to that delta x over x. That's the key right there, right? That's the key right there, right? And don't forget to do our on averages, right? I was getting a little lazy there because that's less of the point right here. You guys should hopefully know that by now, and keep that in mind, right? So, but don't forget it. But I really want to just highlight, this is kind of a weird feeling, right? Kind of like this 1% change. Like, how is this beta 1 times 0.01? It's all right here, right? It's all right here. So let's put some real numbers on this, right? Let's go ahead and put some real numbers on this, and let's go ahead and regress our test score on the log average income, okay? So, and again, part of the reason, what's nice about this, again, there we go, right, is if we think about what that log function looks like, right, that natural log function, and we saw it last class, has that nonlinear shape to it, right, has that nonlinear shape to it. And I'll show you guys that in just a second, okay? So how do we do this? There's nothing fancy, right? We're just gonna take the test score, log average income, comma robust, that's it, Like, and I think it's almost like amazing, right, that we're doing all this, again, kind of back end work. And I'll put Word on there just to get this thing started, right? Doing all of this back end work, but then the actual implementation of this is just so straightforward, right? It's so straightforward. And now we've got this right here, right? 3.62, 5.778. So let's go ahead and write this down, right? This is gonna align, I think, nicely with your lab, right? It should help you actually go through that lab, right? But we've got test score is equal to 557.8. Okay. Then we got 3.8 right here is our standard error, right? And then we have plus 36.42 times the log of income. Okay. So this is going to be 1.4. So very, very significant. Okay. So a couple things to note here, right? A couple things to note, right? The first, I just want to point out the coefficient just because it's a little different, right? And I don't think it's like puzzling or weird or anything like that, right? But beta 0 hat equaling 557.8, right? This implies that the average test score when not income equals 0, but when log income equals 0 is 557.8. Log income equaling 0, well, remember, log 1 is equal to 0. Right, so this is saying when the income is equal to 1, right, the average test score is 557.8. So it's kind of again, just kind of a weird distinction, right? It's something different, not that we're not as accustomed to that. But again, it's not anything to like be upset about or anything like that. It's just simply saying, look, this is where we're centering that regression there, right? That's kind of the leveler. Okay. So then more importantly though, right, beta 1, right? Beta 1 is equal to 36.42. So what does this mean? This is saying as income increases by how much? However much you want, right? You don't have, you can say, you know, very often folks will use a standard deviation, and we can go ahead and do this off the cuff since I pulled the calculator out, I can just go ahead and roll with it, right? You hang out right there, right? So what folks like to do is we'll go to here, and I'm just going to put sum of average income, right? So average income as a standard deviation is 7.2, mean is 15.3. We could take like the square root of that. I'm gonna say 15%, right? So I'm just like kind of just flying by the seat of my pants here. Just like, okay, so I'm gonna have a 15% income increase, right? By 15%, right? And again, kind of recognizing what could go wrong as you kind of expand that percentage difference, right? As income increases by 15%, right? The increase in test scores is 36.42 times 0.15 on average. Okay, you see where I get all that, right? So I've got the 0.15 right here. That's our 15%, 36.42. That's our beta 1. What does this turn out to be, right? I'm kind of doing this the lazy way, right? 36.42 times 0.15, right? That's going to be 5.463 points. So you want to increase your test score by 5.463 points. You've got to increase your income by 15%. Okay. What about if we just take it down to a more, I don't want to say practical, but just a more normalized amount, right? As income increases by 1%, test scores increase by 36.42 times what? Well, whatever 1% is, right? So, oh, I got the 15%. That was just doing numbers in my head. I was thinking about the square root, the standard error, or the variance, Just normalizing a bunch of stuff and then thinking of that as a percentage. So I was just making stuff up, kind of giving a sense of what it could be, right? What kind of an average change in income or an average difference in income could be. So yeah, no, don't worry too much about that, right? Do something like 1%, 5%, something like that. I was just throwing stuff out there. So as income increases by 1%, though, test scores increase by 0.364 points on average. And so back to your point, Jeffrey, I was just looking at the distribution just real quickly in my head and just saw like, is there like if the difference was like 2% between the minimum and the maximum, I'd be like, well, you can't have like a 15% change, but there was a substantial range there, and looked at the average and standard deviation. So here though, right, kind of the more conventional thing to do, just go with like 1%, 5%, 10%, right, something like that, right? So here, right, as income increases by 1%, our test scores are going to go up by 0.364 points on average, okay? Let's translate this into something that is tangible, right? So why is this like a good fit of the data potentially? Okay, well, let's go ahead and let's increase our income by 1% when income equals 15,000. All right, so let's say that, look, we're at a district that has an income of $15,000 per year. If we increase that income by 1%, we should see that that test score go up by 3.364 points. Well, what would 1% of 15,000 be? Well, this would imply, right, 1% of 15,000 is equal to $150. So this would mean if we increase income from 15,000 to 15,150, we're going to increase test scores by 0.364 points, right, on average. Right, so if we have an income of 15,000, why don't we just give everybody $150, right? Give them $150 more in income. That's going to increase those test scores by 0.364 points, right? If you want to increase it by more than 1 point, give them 450, right? That would be 3%, right? So you could go ahead and kind of just extrapolate that forward, right? And it's just in a very straightforward way. Why do I bring this up here at 15,000? Well, because I want to compare it to what happens if our average income is equal to 100,000. Well, in order for us to have an increase of 1%, that means that the change in X needs to be 1,000, right? Because the reason is that if you have $100,000 in income, a 1% increase takes you to 101,000, right? So if we increase income, right, increase income from 100K to 101K, right, we increase our test score by 0.364, right, the same amount, right? So if you think about this, what's neat is that we just simply said, look, we increase income by 1%, we increase test scores by 0.364 points, right? That's a very straightforward interpretation compared to the polynomial stuff, right? The polynomial stuff was like, geez, there's just like tons of like potential spots that we could go and look at the differences. But by saying this, 1% increase in test score or in income increases test scores by 0.364 points, we're saying, hey, if you have $15,000, increase income by 150, you'll increase test scores by 0.364 points. At the same time, though, we're also saying increase income by 1,000 when your average income is 100,000, you get the same increase in test score, right? We're seeing this, you need a bigger change in X to get the same change in Y, right? So you can just almost see the numbers decreasing the slope, right? The slope is going down, it's getting flatter, right, as we increase our X here, okay? So let's go ahead and let's show this, right? So just to give you guys, again, just more exposure to commands, right? I think it's always nice to have that. So we're going to run this regression, test score on log average income, and then we're going to just predict, I'm just going to call it case one, right? Because this is our first case, right? And what is that doing? That's taking all of our x's, right? And essentially just saying, okay, let's predict what that y would be. And then I'm going to take we'll do a two-way, and I'll just do scatter because it's easy enough, right? And I'm just going to do case one on our log average income, okay? Take a look and see what this looks like. Ooh, it looks like a straight line, right? So why does that look like a straight line, right? Because essentially what we've done is that logging that x, like we're essentially linearizing that relationship, but that's not what we want, right? What we really want is we want to say, why don't we take the two-way and scatter and do case one and average income, right? Let's take a look at this here. That looks a lot nicer, right? That looks kind of like what that data is saying. So, and if we were to take this and let's go ahead and do another scatter right on top of this of, let's do test score and average income, right? This is kind of neat here. There we go, right? And so, can I do a line? I'm like worried. You guys are gonna laugh at me if I do this. I think this could really backfire. So I'm saying it right now. It could backfire. No red marks. So what's happening is, yeah, I need to put it in order. So I kind of like this guy better. Okay. So yeah, so this is all we need, right? This is all we need, and we could go ahead and mess with it. We can make it. There's a way to make it a line. I can show you guys that later, right? But ultimately, I'm just plotting all the predicted values right here. That's going to be in blue, and then I've got the actual test scores in red. And if I wanted to make the predicted values be above the test score, then we can just go ahead and do that. There we go. That looks a lot better. Fitting that data kind of nicely now, right? That's a nice fit of the data, right? Just with that log function, right? Just with that log function, okay? So again, just some more commands, just messing around. Always good to see it. I'm going to always give you guys a chance to look at that or see that when we have an opportunity. Okay, last part of this, right? Last part of this. So we've got yi equal to beta 0 plus beta 1 log xi plus ui, okay? So if we were to say, what is beta 1? And this is where that straight line came into play right here. I'll just actually bring that back up because it actually is kind of interesting to see this be so straight. Like, why is this so straight? So straight. All right, well, the reason this is the case is because we've linearized the relationship between log of x and y, right? So log of x, y, this should be a straight line. It has to be a straight line. That's why I brought it up in the first place. But what is this actually saying? It's saying the change in y over the change in the log of x. That's what beta 1 is representing. Just like before, remember it was a change in y over the change in x. That's what beta 1 was telling us, is literally that slope. Here, it's that change in y over the change in ln of x, okay? So this seems like a kind of an innocuous or like kind of irrelevant difference here. But if we take this a step further, this is actually the change in y over the change in x over x, right? That's what the change in the log of y is telling us. So this is actually the change in y over, not the change in x, but the percent change in x right there. So that's kind of cool, right? So it's like we could have just started with that. You could have all believed me and whatnot, but it's nice to kind of see the development of it. But here we've got the change in y over percent change in x, right? And so that came just from this regression right here, just like before, right? Don't write this down, but remember we had y equal to beta 0 plus beta 1 x plus u. Well, beta 1 is equal to change in y over the change in x, right? Just a slope. That's the same thing here. We just got a different x and it has a different meaning to it, okay? So, all right, I'm gonna erase that because that was like from week 2. Okay. All right, that's case 1, right? That's case 1. So if you got questions, fire away, right? But hopefully this is feeling like a little bit more comfortable. Hopefully you're seeing that this isn't quite as intense, right, as the start of the term, because we have such a good understanding of just basic regression analysis. Now we're just messing with our x's, right? Let's mess with the y's now, right? Let's look at case 2 where we have y and logs, x is linear. So your book calls it the log Lin regression. I put it there because that's what your book says. I have never heard anybody say, oh, I'm going to run a log Lin regression. Like, it just is not in the nomenclature. But, you know, I'll be consistent, okay? So why would we ever do this, right? Why would we ever want to say, like, okay, we have this nonlinear relationship between x and y, right? But why wouldn't we just make x log? Why not always log x? Why not always use ln of x? Okay. Well, the thing I'm going to tell you, I'm going to bring it back to some work that I've done after I show you what's going on with the test score, right? But ultimately, all right, the log of 0 is equal to negative infinity, right? So, and that makes sense, right? Because if we go from 0 to 1, the log of 0 to the log of 1, right? This is like an infinite increase, right? So nominally, you just can go from 0 to 1, right? But you're going from nothing to something. That's an infinite increase in your variable. So whenever you have a log function, you actually can't have zeros or negatives, right? So you cannot have, we'll say, our log, we'll put it this way, cannot have x less than or equal to 0 when using the log of x. Same thing with y, right? So you can't have a 0 or a negative value and take the natural log. It's just, it won't come out. It's indeterminate. So now we have this infinite increase in a variable. When we have x equal to 0, it's not going to be relevant to us. This is particularly important when you're trying to measure the effect of a policy, right? So when you measure a policy change, very often you're just simply saying, right, the policy is equal to 0 if no policy, 1 if policy, right? So I'm going to tell you about a law change that I took a look at when I was in grad school. I can't take the log of 0 to the log of 1 to see the effect of the policy. You just do 0 to 1, right? The policy is either on or off, right? And so you would never want to take a log model for that. But if you want to fit a nonlinear relationship, yeah, you need y in your logs, x as your linear variable, okay? Okay, so this is the one motivation for it, right? One motivation for it, but I think it's really important. And like I said, we'll come back to it in just a second, right? But when we have this, right, what regression are we running? We're running the log of y on beta 0 plus beta 1 xi, okay? So this is a little bit of a kind of weird relationship, because what we're getting is we're getting this kind of percentage difference in the y, but it's a linear difference in our x. So this means that a 1 unit change in x changes y by how much? And we'll see this come out, right? And I'll do the numbers behind it, right? But it changes it by 100 times beta 1%, right? And I'll be correct on this, on average, okay? So we're going to take beta 1 and we're simply going to turn it into a percentage. That's all we're going to do, okay? So how can we do that, or why can we do that? Why is that allowed? Well, what we're doing is we're taking the log of y plus delta y, right? That's where we're going to end up. We're going to start at y. This is going to come from taking beta 0 plus beta 1, not log of x, but x plus delta x minus beta 0 plus beta 1 x. Okay, so what I've done there is I've said, look, start at x and y, right? So we're at x and y, right? So log of y is equal to beta 0 plus beta 1 x. The u is going to be expected to be 0, right? We increase our x to delta by delta x, right? So we have x plus delta x now. Then what happens to the outcome? Well, we've got log of y plus delta y, right? And so then when we put this together, this right here is going to be delta y over y, right? That's the whole point of using these logs, right? Lots of this stuff cancel out, and we just end up with beta 1 times the change in x. So if we were to translate this, right, we would say, well, this is just the percentage change in y is equal to beta 1 times the change in x. So if we change x by 1 unit, right, we change x by 1 unit, that's going to give us the percentage change in y, right? And so that's why we say, look, it's just 100 times, we're just converting beta 1 to a percentage, right? And so multiply it by 100 because that change in x is 1, which is making it a percent, right? And so now we got this percentage change in y, okay? So let's go ahead and see this in action, right? Let's go ahead and see this in action, right? And let's go ahead and regress our log of test score on average income, okay? So we can go ahead and generate log test score equal to ln of test score, right? So hopefully you guys have gotten just comfortable with the generation of variables. There's nothing crazy or fancy about it, right? Just gen, name of the variable that you want it to be, can be anything you want, right? Obviously you want to make it something that's easy to follow. And then we've got the log, ln, natural log of test score. So from there, just run that regression of log test score on our average income, comma robust. Then we'll go ahead and do outreg 2, just go straight there using lecture 14, comma word, okay? So let me go ahead and run this. Everything's coming up, coming up, coming up. And let me grab this and this. Okay. So what do we get? Well, now notice that we get the same coefficient that we had essentially in this first regression, right? We get this beta 1 coefficient on average income, right? Because that's what we're running. We're running beta 1 times average income, but we're getting a log outcome. And so where's the difference? The difference is right here, right? We go from test score to log test score, okay? So when we run this, what do we get? We get log test score, all right, is equal to 6.439, right? And put a hat there, right? And then we're going to have a 0.0029 underneath, plus 0.00284, right, times that average income, okay? And this is very significant, right? Very significant. Right, and I know that because I'm like writing down an extra 0, like it's an order of magnitude more significant. We got a p-value of 0, but we got t-stat of 16.24. Okay. All right. So what does this mean? Right. Well, we can say, you know, beta 0 is really an odd interpretation here, right? Because beta 0 is saying, well, the average income is 0. What's the log of the test score? Right. It's 6.439. Right, but that has like just we have no idea kind of what that means. It's just the log of the average test score, right? But really, I think the thing to highlight is beta 1, right? So beta 1 here is going to be equal to 0.0028. I'm going to get rid of that 4 there, okay? And so what does that mean? That means that when we increase average income by 1 unit, in this case, this would be $1,000, right? We expect the test score to increase by how much? Well, we would increase by 100 times beta 1 hat, which is equal to 100 times 0.0028 or 0.28% on average. Okay. 0.28% on average. Right. So there's, again, it comes off as, I think, kind of awkward, like looking at this, and especially when I generalize this, just looking up, this is everything right here, right? A 1 unit change in X changes Y by 100 times beta 1% on average. Like that doesn't feel, I don't think that's like a comfortable line, right? It's not like, oh, this is just a slope, right? It doesn't have that kind of natural feeling. However, right, when we just look at this number, we would just say like, well, what's the percentage of that? Like that's 0.00284, that's 0.2%, right, or 0.28%, right? We can just look at it, and so despite what's going on beneath it, right, it's actually like a pretty straightforward interpretation. And so to that end, right, this is actually the regression that I used in my dissertation, the main paper in my dissertation. And in my dissertation, what I looked at was I looked at the log of suicide rates in a state, and I ran it against beta 0 constant, and then I've got my beta 1 at, I'll put plus beta 1 here, times, this would be an insurance law, right? And this was actually a mental health insurance law, okay? This was actually my, like I said, this is my dissertation, and it actually is this paper right here, right? And so I actually presented this paper right here, and I don't want to make it seem like I did anything actually that like meaningful. Like I think it's an important question, right? This is not to like brag. This is to show you guys that I'm doing exactly what I'm showing you here. So what am I showing? I'm saying, okay, there's this access to parity law, or the mental health insurance law, okay? And so kind of just draw your attention to right here, column 2. Right, column 2, I've got a negative 0.04 coefficient, right? And then what's my dependent variable? The dependent variable is the log suicide rate. So I could present this, and actually people could just look at this table and say like, oh, I see exactly what's going on. Like I know what he means, right? When I look at this table, it means that when these laws are enacted, we've got a reduction in the suicide rate of how much? Well, it's a log suicide rate, so I'm just going to take this 0.04 and just turn to a percent. That's all it is. Right, so the interpretation became very straightforward. I could just say, hey, there's 5%, 4%, 7%. That's the robustness of it, right? By saying, okay, let me do this in a bunch of different ways, show you guys there's a different set of states, right? There's a different set of ways to code the laws, but we're getting this 5%, 4%, 6%, 7% reduction every single time, right? So however we cut the data, or however we want to look at this, we get the same effect. And I think that's it makes that interpretation just that much easier. So for here, we would say beta 1 hat was a negative 0.04. So what this means is that the suicide rate in state I is 4% or 0.04 times 100 lower after enacting a mental health law, right? Mental health insurance law, right? So I think it was kind of, again, nice to be able to see this in a clean way. Obviously led to a lot of discussion. It's certainly, I think, an important topic that deserves a lot more attention, right? But it was at least a start, right? It was a start. It got folks rolling on this topic more so than I thought it would. So just showing you guys that this is not something that I'm just showing you to make things go difficult, right? So a question came up in chat, like, why does it change from 0.05 to 0.07 to 0.05, 0.04, 0.07? I can tell you exactly why, right? I better be able to tell you exactly why, right? This was like what I got my first job with, right? And so what you have to do, and this is great for you guys to see, and I can make this a little bit bigger. This information right here and this information in the table is telling you what's different between column 1 through column 4. So column 1, and I had gone through this in the paper, as I said, look, there's states that have these laws, right? These kind of these full laws, and the access to parity law. What that means is that if you have health insurance, the state is requiring you to have health insurance for mental health and physical health at the same level, right? So if your co-payment for health insurance is 2080, right? You pay 20%. Health insurance pays 80%. If you go to a psychologist, it has to be the same condition, right? There's the same match. It has to match, right? There has to be parity between those two, and so you'll pay 20%. Health insurance company matches 80%, right? So whether you break a leg or whether you go see a psychologist, you're getting covered the same way. So that's what that means right here. The non-parity law is different in that it says you have to have some mental health care, but it doesn't necessarily need to be at parity. Okay, and so then there's states with no law. Okay, and so what you can think of here is that this is saying, look, if a state goes from no law to an access to parity law, they're going to see their suicide rate go down, or the suicide rate did go down by 5%. Right? And then if there was a non-parity law, there was essentially no change, right? You don't ever say that it was like positive, like it wasn't that it went up. It was just this is just noise, right? There's just insignificant relationship. So that was what I showed you here, right, with all states. But then what I did is I said, why don't I just look at the parity states, right? The states that actually enacted these stronger laws, right? Because they enacted them in different years. So we've got this reduction of 4%. Right, if we just look at compare states, right, these access to parity law states, right, they're all similar in the fact that they enacted a parity law. When we just isolate it to that group, right, we've got this reduction of 4%. So it's a different coefficient because we got a different comparison group is ultimately what it is. And we would expect it to go down somewhat because we're comparing states that are very similar in column 2 versus states that are less similar in column 1. Column 3 breaks them down into, there was 3 different kinds of laws. There was strong, like these were your access to parity laws, these two, and then there was this weak law right here. So, and then this was no law. So, and then this one right here just grouped the 2 stronger laws into 1 law. So, yeah, so I haven't explained that for like 10 years, but I still got it. So it didn't leave me. When you do a dissertation, it doesn't leave you. So, but yeah, no, it's great to see. So, I think it's a fine example because it goes to show that, and this is something that people have picked up on, and you don't need to have, an overly complicated approach to try to answer a question that I think is important. So, okay, enough about me. Let's go back to test scores. Let's go back to case 3. The case 3 won't take so long, and the reason, and you guys will see why, is because ultimately with case three, it's not, it's almost like going against what we were trying to do in the first place. Okay, so case 3 is when both x and y are in logs. So again, your book calls this a log regression. I do not know where they come up with that stuff. Like, I don't know where they heard it, but if they did, then they're not lying, right? So what is this regression though? This is log of y is equal to beta 0 plus beta 1 log of x plus ui, okay? And so what you can kind of see and what you can kind of guess right here, just like we did in the previous cases, is that beta 1 will be equal to the change in the log of y over the change in the log of x. So this will be the change in y over y, change in x over x. So this will be the percent change in y over the percent change in x. Okay. So when we see something like that, what's kind of, there's 2 things that I think are important to highlight before we kind of get into the details of it, right? But beta 1 hat is going to tell us that there's a 1% change in x, which will lead to a change in y of beta 1%, right? We got percentage changes on both sides here, so our beta 1 will tell us, hey, x changes by 1%, y is going to change by beta 1%, okay? So we've got kind of that percentage just through and through. Now, the other thing I want to draw your attention to is this right here, okay? Change in y over y divided by the change in x over x. You might be saying to yourself, like, gosh, this looks really familiar. Like just this change in something over something divided by the change in something over something. Like possibly the change in in quantity over quantity, change in price over price. Doesn't this feel a little bit like elasticity? Like this is like the elasticity formula here, right? And so it is exactly that. And we would say that beta 1 is actually the elasticity of y with respect to x, right? So we can go ahead and say right off the bat that when we run a log regression, right, that's what I think of it as, well, log, not a log, but run a log regression, right? So we got log y and log x. Beta 1 will give us an elasticity. So that's kind of neat, right? It's kind of neat to just say the regression coefficient will be the elasticity of y. How much does y respond to a change in x in percentage terms, which is exactly what elasticity is, right? So when you think of elasticity of demand, how much does price change with regards to quantity, right? That's exactly what it is, okay? So when we think about this interpretation, though, let's go back to the way we've been constructing this and say, you know, we're going to end up at the log of y plus delta y after starting at the log of y, right? That's where we're going to end up, right? That's going to come from beta 0 plus beta 1 log of x plus delta x minus beta 0 plus beta 1 times the log of x, okay? So what we have here essentially is case 2, and over here we've got case 1. So we've combined these two cases, obviously, right? First one was log x's, second one was log y's, now we've got logs of both, right? But what it tells us is that we have a change in y over y equal to beta 1 times the change in x over x. So when I said that beta 1 was just what we have up here, well, that just comes from this derivation right here, the percentage change in y over the percentage change in x. Okay. So when we run this, we're going to run the log of test score, right? The test score I right here. This is equal to beta 0 plus beta 1 times, let's go ahead and do, we'll stick with log average income, right? Log income, right? Plus UI, okay? So let's go ahead and roll with this here, right? How would we do this, right? So now we're going to regress log test score on log, on log average income, and we don't have to generate anything. We've done all the work there. Log test score, log average income, robust, outreg 2 using lecture 14, comma, word. And I want to do something. I know what I'm doing, and I just want to show you guys, no panic, right? File using lecture 14 is read-only, cannot be modified. This is just like, when I first read this is just like, it's like Stata's like, what's wrong with you? I'm like, just tell me what I should do, right? Like it like demeans you, and then it says like, all you need to do is close this. Like you could have just told me to close Word. Like that's all you need to do, right? So so again, I knew that was coming. I saw a little Word file down there. So again, just always never panic, right? When you see that red mark, just kind of read through it and just know that the answer is usually kind of in that red mark. Okay. All right. So what do we get here? We get log test score. This is equal to 6.336 plus 0.0554 times log income. And I'm just going to put a hat on there. Not going to worry about the standard errors. Those are they're very significant. Okay. So now, right, with our beta 1 equaling 0.0554, what is this telling us? This is telling us that there's a 1% increase in income, right? So we're using this percentage changes, right? So 1% change in income, right, is expected to increase test scores by how much? Well, look up above here, right? A 1% change in X changes Y, right? Changes, I should just put changes Y. Hold on. Changes Y by beta 1%. Okay, so expected to increase test scores by how much? Well, it's expected to increase test scores by beta 0.5%. So does that mean that this is just 0.0554%? Yep, that's what it is, right? No need to overcomplicate it, right? So this will be on average. I'll make that, keep that consistent there, right? So we increase income by 1%, increase test scores by 0.05%. Does that make sense? I don't think that, I don't have like a context for it, but it seems reasonable, right? A 1% increase in income isn't a lot, right? And so then we're increasing test scores by 0.05. Maybe a better thing to do, even though it kind of makes the log difference be called into question, right? We would say a 10% increase in income is expected to increase test scores by how much? Well, we would say this is going to be 10 times 0.0554%, right? So before we implicitly did just 1 times beta 1, right? Here, we're going to do 10 times beta 1, right? So this will be equal to 0.554% on average. Okay, so not a full percent up, right? You're not going to go from 700 to 707. You go from 700 to 703.5, right? Why do we need to multiply it by 0.0554 by 100, like in case number 2? Good question. And the reason is because you've already got the percentage wrapped into your change in X. Good question. Really, really good question. And I feel the same way. Like every time I kind of get ready for this lecture, I'm like, why don't we do that again? Oh yeah, because it's already there, right? It's literally already there, and it's a weird. It's kind of like it's snuck in there, but your percentage is already there. Notice above in case 2, and this is a great point, right? We didn't have the percentage there, right? It was a 1 unit change in X. Now we've got to turn that into a percentage, right? That's the deal. And it's again a really subtle point. The fact that that's noticed, it's kind of a heartwarming question. I appreciate it. So let me just in the last 2 minutes here, let me just summarize this, because this is a great kind of ending point here, right? So we've got our 3 cases, right? And we can go ahead and say, well, the specifications with these 3 cases, right? They all have different interpretations, but notice how they're all like we're not plugging in numbers necessarily to get some meaning out of it. I did in case 1 because I was wanting to show you, hey, this is what you can do to convert this back to a nominal change. Right? But there was nothing that was like the interpretation as a whole didn't change, right? We just had yi equal to beta 0 plus beta 1 ln of xi plus ui, and then the interpretation that we had of our beta 1 was just saying we'll say a 1% change in X led to a 0.01 times beta 1 change in Y. Okay, so it's a little small, so I'll make this a little bit bigger here. All right, for the second specification, we had log of Y equal to beta 0 plus beta 1 xi plus ui, which is saying a 1 unit, we'll do 1 unit. 1 unit change in X leads to a 100 times beta 1% change in Y. Okay. And then the last one is log of X is equal to beta 0 plus beta 1 ln of X plus ui, which is a 1% change in X leads to a beta 1% change in Y. Right, so the whole day can actually be characterized by this table right here. And again, if I was to write this down and move on, you guys could say, yeah, I guess I get it, but you might not get it, right? Like it might be a little bit more difficult to get. Now you can kind of look at this and say, like, yeah, I kind of can see every single part of this. So and every single part of each specification, know how to interpret that. So if you're feeling good about this, I can say that your quiz, your quiz that's coming up, not Thursday anymore, but now Tuesday, you actually do have you can go ahead and give it a try if you would like, depending on your timing, but don't feel like you need to. If you feel better about waiting until after class on Thursday, you obviously have more than enough time. But I think this is a perfect place to stop because one of the big limitations that we talked about is the log of 0 is negative infinity. So if we have a lot of values that are equal to 0 or 1, but we have a nonlinear, or 0 or negative, but we have a nonlinear relationship, how do we fit that? Right. So what we're going to see next class is we're going to see alternative ways to fit nonlinear relationships, and I think again it's kind of part of this bigger story that I like. I like the feeling of that type of class more than just kind of definitional stuff. So we'll be tackling more questions and more problems as we move through the rest of the term. So guys, I think that's a great ending point. I like the questions. I hope you guys. I hope this all kind of made sense. Everything came together. If it wasn't already, and you guys are just hanging in there, and it'll be end of week 8 before we know it. I can't believe it. Crazy stuff. So, all right. So I'll be at office hours in like 10, 15 minutes or something, and we can chat, hang out there, and I'll talk to you guys soon. All right, guys. Stay safe, stay healthy. We'll see you guys on Thursday. See ya. Thanks, guys. I'm gonna save all this stuff, post it all, save this lecture 14 do file. Here we go.